Welcome to Section 8 of Introduction to Image Processing. This section is about geometric operations like cropping and padding and rotating and resizing and other operations that work at least conceptually by changing the locations of pixels without changing the pixels. Although the focus of this section is on doing these operations in computer programs, many geometric operations can, of course, also be done interactively. For example, resizing an image can be done by clicking to select the image and then clicking and dragging one of the handles around the border of the image. Other geometric operations can be applied using buttons and dialog boxes. For example, below the selected image is a row of buttons for various operations. The second button is a cropping tool. Clicking that button brings up an outline that can be adjusted by clicking and dragging to select part of the image. After that, selecting the crop button crops the image down to the selected part of the image. Interactive operations like this are very useful, of course, but there are also applications where, for one reason or another, these operations must be done automatically, and so for every interactive operation, there is always a way of doing the same thing from within a computer program. For example, resizing an image can be done using a function called image resize. Here is an image that starts out with 150 rows and 200 columns of pixels. This uses the image resize function to resize that image to get a result with 400 columns instead of 200, and to preserve the aspect ratio of the original image, it also doubles the number of rows from 150 to 300. The aspect ratio is the ratio of the height to the width of the image. It is possible to specify width and height at the same time as in this example, but unless the numbers are chosen carefully, this generally results in a distorted image. To preserve the aspect ratio but specify the height rather than the width can be set to automatic. For example, this specifies a height of 30 and a width of automatic, which gives a result with a height of 30 and a width that is adjusted to be whatever it has to be so as to preserve the aspect ratio. It is worth noting here that interactively stretching the image on the computer screen does not usually change the size of the image inside the computer. For example, although this image can be stretched to be much bigger on the computer screen, the image dimensions function will still report that this is a 40 by 30 image, since that is the size of this image as stored inside the computer. The size of the image on the computer screen is determined by many often system-dependent things such as preference settings, hardware and option settings, and so on. Resizing an image usually involves increasing or decreasing the number of pixels, which requires some sort of interpolation to work out values for the new pixels. For example, here is an artificial image with just 2 pixels. And this result shows a resizing of that image to a width of 12 using linear interpolation to calculate values for the new pixels. In image processing, this interpolation is called resampling, and so the choice of interpolation method is set using the resampling option. This shows the interpolated shades of gray. The image data also shows the interpolation between the original pixel values. There are many other common methods of resampling. Here is an example that shows what is called nearest neighbor resampling, which works by copying the pixel value from the original image that most closely aligns with the corresponding pixel in the resized image. The image data shows that the resized image actually consists of many copies of the original pixel values. The choice of resampling method can also make a difference when making an image smaller, although often the only obvious effects are that the smaller image uses less computer memory and has less resolution of fine details. For example, here is a 512 by 512 image, and this uses the image resize function to get a 32 by 32 image, such as might be done to create a thumbnail image. This result can be stretched on the computer screen, but stretching does not change the fact that this is still a 32 by 32 image, so the image has a pixelated appearance, where the individual pixels are visible as small squares of uniform color. That 32 by 32 image can be resized back up to 512 by 512 using the image resize function. This shows the resizing done using nearest neighbor resampling. The result is a 512 by 512 image, but it has the same pixelated appearance as the 32 by 32 image because nearest neighbor resampling increases the number of pixels by simply making lots of copies of the pixel values from the smaller image. For comparison, this shows resizing using linear resampling. The result has a blurry appearance since it isn't possible to recover all of the detail of the original 512 by 512 image from a 32 by 32 grid of pixels, but the averaging eliminates the obvious pixelation. There are dozens of other common methods of resampling. For example, this shows resizing with the resampling option set to cubic, which uses cubic splines for the resampling and seems to give a slightly better result for this image. The choice of resampling method can sometimes affect important aspects of the result. To illustrate some of the things that can happen, here is another artificial image showing two white lines on a black background. This is a 41 by 41 image. Resizing this image using cubic resampling, or for that matter almost any method that involves interpolation over more than one pixel, will result in a fairly dark image. The interpolations are weighted averages, and most of the pixels in the original image are black, so the averages will tend to be quite dark. The image can be made lighter using the image adjust function to stretch out the range of pixel values. The result reveals a pattern of bands of different shades of gray that were not present in the original image. These extra bands are artifacts of the resampling. In this example, those bands result from the curves in the polynomials that were used in the cubic spline interpolation. One detail of resizing where artifacts like this can sometimes show up is in the handling of pixels at the outer border of an image. For example, here is a 200 by 128 image. Resizing that image with linear resampling to get a 50 by 32 image requires interpolation between pixel values, which for pixels at the edge of the image means somehow, at least implicitly, padding the image by a few pixels to get pixel values beyond the edges of the image. The image resize function has a padding option to specify that padding. Here is an example where that padding is set to black, which gives a result with a row of darker pixels around the border of the image. This happens as a result of the interpolation between the pixels of the image and the black pixels specified by the padding option. Rather than padding the image with black pixels, a more common approach is, before resizing, to essentially pad the image by reflecting the image through the image boundaries. The resizing is then in effect done on the padded image and then cropped after resizing to remove the padding. Many of the same issues with artifacts of resampling that come up for image resizing also come up for image rotation. For example, this shows an image given a slight 2-degree rotation using nearest neighbor resampling. The third argument of 512 in the image rotate function here is included to hold the rotated image to a width of 512 pixels. Now modify that input to do 180 of those rotations in succession, which in principle should get back to the original image, but the repeated rotations with nearest neighbor resampling introduce some rather dramatic artifacts. Now try the same operation, but with a resampling method called OMOMS, which stands for Optimal Sampling of Maximal Order and Minimal Support, which won't be described in more detail here, but after the same repeated rotations with this resampling method, the artifacts are almost invisible. It isn't possible to completely eliminate artifacts of resampling, but it is usually possible to find an algorithm where the artifacts do not affect the features that are of interest in particular applications. Another basic geometric operation is cropping, which can be done interactively as was shown earlier by clicking and dragging to select part of the image, and there are also several ways of cropping an image as part of a program. One image cropping tool is the image crop function, which is useful when the cropping is specified by giving the size of the result. For example, here is an image with dimensions 1920 by 1280, and this shows the image crop function used to crop that image to a result with dimensions 300 by 400 by cropping symmetrically from the sides and from the top and from the bottom of the original image. Another method of cropping is cropping to include selected points in an image, which can be done using the image trim function. For example, points in an image can be selected interactively. Then copy the coordinates of those points and paste those coordinates into the second argument of the image trim function to crop the image to be just large enough to include the selected points. Cropping can also be done by directly specifying the number of rows or columns of pixels to remove, which can be done using negative padding in the image pad function. For example, here is a manipulate that shows pixels being added around an image when the second argument of the image pad function is positive, and pixels being removed when the second argument is negative. Cropping can also be done by operating directly on the underlying image data although the coordinates for operations on the image data array are not the same as the coordinates for operations on the image. For example, this shows cropping using the take function applied to the image data. This takes the first 40 rows and the first 90 columns of the image data array, which gives the upper left corner of the image. Equivalently, this can be done using the image take function. The take function and the image take function use array coordinates rather than image coordinates. To see why that makes a difference, here is an equivalent cropping done using the image trim function, where the 2 points specified in the second argument of the image trim function are the coordinates of the corners of the cropped area. The image trim function uses image coordinates. In image coordinates, the pixel in the lower left corner is identified as 1, 1. The pixel in the upper corner of the cropped area is at coordinates 1, 100, and the pixel in the lower corner is 90 pixels horizontally and 60 pixels up, giving the point 90, 60. The image take function, on the other hand, which is based on the take function, uses array coordinates. With array coordinates, the 1, 1 pixel is in the upper left corner. The vertical coordinates are given first and count down from the top, so 1 through 40 takes the top 40 rows of pixels. The horizontal coordinate is given after that, so 1 through 90 takes the first 90 columns of pixels. The array coordinates of the pixel in the lower corner of the cropped area are 40, 90. These differences are all just differences in convention. They are something to keep in mind in image processing programs that use functions like image take that are based on array operations, or in programs that operate directly on the image data array. So far, all of the cropping examples have involved somehow entering the cropping specifications, but in many applications it is useful if the cropping can be worked out automatically by the computer. For example, here is an image that can be cropped to be just large enough to include the bird. The cropping could be done like this, by entering arguments to describe exactly how much cropping to do on each side of the image, but if there is a large number of images to be processed, then it would be nice to have the computer work out the cropping. One situation where it is relatively easy to do that occurs when the border to be cropped has a nearly uniform color. It turns out that the image crop function is already programmed to do that sort of thing, at least in simple examples. For this image, just entering image crop with no additional arguments does the necessary cropping to remove the uniform border. Another strategy that amounts to the same thing but that exposes some details of the process is to use the border dimensions function, which provides a variable for specifying the amount of variation that is allowed for pixels to be still considered part of the border. For example, this shows the border dimensions function applied to this image with a second argument of 0.02, which is the argument that specifies the allowed variation in the border pixels. The result is a list giving the amount of cropping to be done on each side of the image. That result could be used in the image crop function, but it turns out to be easier to treat this as an image padding problem with negative padding. For example, this shows the necessary cropping done using image pad and the border dimensions function with negative padding indicated by the minus sign in front of the border dimensions function. Here the cropping seems a bit tight around the birds, so some extra padding can be added by adding to the second argument of the image pad function. For example, this adds an extra 10 pixels around the cropped image. Another situation where it is relatively easy to have the computer work out the cropping comes up when there is some way of identifying key points or points of interest in an image. Finding key points in an image can be a complicated problem, but there are nevertheless many tools available to do it. Once the key points have been identified, the image can be cropped by simply trimming the image to be large enough to include all of the key points. To show how that can work, this shows the image key points function applied to an image from an earlier example. The result is a list of points that have been identified as points of interest by the image key points function. To help make sense of the key points, this input displays the key points as red dots on the image. This input also includes the key point strength option, which restricts the result to only the more prominent key points. The image can then be cropped by using the image trim function to trim the image to be just large enough to include only those key points. You can also cluster the key points to select several parts of an image. For example, consider cropping to isolate the 4 birds in this image. Here is a manipulate input that sets up a slider for adjusting the key point strength. In this example, a key point strength of about 0.002 gives key points on the birds. Since there are now 4 distinct sets of key points, it is sensible to cluster the key points. This shows the clustering done using the find clusters function. The key points have now been organized into 4 clusters. This shows the image highlighted with the key points in each cluster. From there, it is easy enough to trim the image around each cluster of key points. The cropping is again a little bit tight around each bird, so this modifies that input to add 30 pixels of padding around each of the trimmed images. There are many other more complex geometric operations that are often just combinations of cropping, resizing, and rotating, sometimes applying different operations to different parts of an image. The details of these more complicated operations will not be explored here, but the basic ideas are usually straightforward. As an example of one such operation, here are 2 images set up as the values of I1 and I2 that show our overlapping views of the same scene from different perspectives. This uses a function called find geometric transform that works out the rotating and resizing needed to get the second image to line up with the first image. The result is a transformation function that can be applied to the second image to get an image where different parts of the image have been rotated and resized as needed to align with the first image. The 2 images can then be stitched together into a single image. That's the end of the examples for this section. To summarize, here are some of the topics from this section. If you are interested in learning more about the more elaborate geometric operations like the perspective transform that was mentioned only briefly here, a good place to start is by learning about find geometric transform, image perspective transformation, and related functions.